Alright guys, so this is our lesson 2.12. The notes look a little bit different this time, and the way we're going to do the notes is also a little bit different. Usually with notes, it's all about me telling you, what to do and how to do it, and then let you practice. But really, the majority of this lesson is really just, I'm going to do some quick explanation for you, but most of this is going to be you guys practicing, okay? So the purpose of this lesson 2.12 is to teach you guys how to take a big group of different types of integrals. If you take a look at your second page of your notes that we printed out today, how to look at a big group of integrals. All of these integrals are similar, but yet the way you do the integration is different. And so what I want you guys to do today is I'm going to be teaching you guys how you can tell what strategies to use and when to use those strategies, and also review the strategies with you. And then your homework for tonight is just going to be a repeat of this exercise. It's going to be your responsibility to figure out what strategy do I use, and then you're going to use it, okay? Because we've learned quite a few. Now, this worksheet is not, or this lesson is not intended to help you know how to do all different types of integrals that we've learned, but really just the ones that are really easy to get confused and mixed together, okay? And the ones that we're going to be focusing on today are rationals. What is a rational expression or a rational integrand? It's any time you have a fraction. Notice all of these are fractions. All right? And so because they're all fractions, they all look very similar. But yet the way you integrate these is a little bit different. And so I'm going to teach you guys how to look for the different characteristics in each one of these so that you can rightly know how to solve each one. Okay, so this is the lesson, once again, where I'm going to teach you guys how to know what strategy to use and when to use it. And that's what this first page is all about. All right, so let's begin here. Part 1. Now, the first kind I want to talk about are these ones that are really basic looking. The ones where you have just a number on the top. Now, it doesn't have to be a 1. It could be any number, but so long as it's just a number, not a variable, but a number. And then you have an x on the bottom with a power, okay? There might even be a coefficient here in the front of it, but it doesn't matter. So long as you have a number on the top and just a single term on the bottom with a power, I'm going to show you guys two different types that you should be aware of at this point, okay? So, whenever you have in the denominator the power is just a 1, so like if the n was just a 1, in which case if the n was a 1, they wouldn't even bother writing it honestly, so I'll just delete that really quick. But when you have just 1 over x, what that is that's an ln problem, okay? If it's any other power, like if this was a 2 for instance, a power of 2, like x squared, then you're going to do the reverse power rule, okay? So what I want you guys to do now is I want you to take a look at part 1 here. That's this. I want you to pause the video, and I want you to write both of these problems in the appropriate spot. And what do I mean by that? Up here, I want you to put one of them in this spot and one of them in this spot so that you'll know which one is which. So which one of these integrals down here under part 1 would be a natural log, and which one would be a reverse power rule? And it all has to do with, does it have a power of 1 in the bottom or a different power? So you guys pause the video here and give it a try, see what you can get. Okay, so here they are. So we have the one that is a natural logarithm is the negative 20 over x, and that's because the x is a power of 1. The other one has a power of 3, and when we have those, it's a reverse power rule. Now here's what I want you guys to do. I want you to take a moment and see if you can integrate these problems. Now if you can't, if you don't remember, it's okay. You can skip them. I'll go over them. But I do want you guys to take this opportunity to try to refresh your minds on how to do this stuff. So if you can, pause the video and see if you know how to work out both of those integrals. And when you unpause it, I will then go over it. All right, so for number 1, I'm going to go over it now. Well, not number 1, but for this one here. That's what I mean by number 1. Since the power on the bottom is just a 1, we know this is an ln. But before you begin an ln problem, what you want to do is you want to take out any constant multipliers, because it's really just supposed to be 1 over x, not anything else. So take those out. Same thing applies if you had a number down here. If there was like a 3 there, then you would just take the 3 out also. But we don't have the 3, so I'm going to erase that, but I was just making a point. All right, so there's that. And then we go ahead and take the absolute value of x there and put a plus c, and we're good to go. So that is the ln problem. Now let's take a look at the other one. Now, as I mentioned, that's a reverse power rule, and we know that because the power is something other than 1. So when we have that, here's how we handle those situations. You could take the 6 out still, but it's not necessary. What we really want to do on these ones is we want to really take this x to the 3rd and move it to the top with an opposite sign. And then all we have to do is the reverse power rule. So we would add 1 to the power, and then we would divide by that value. And then don't forget your plus c. Now, of course, a lot of times you're going to need to simplify these a little bit. So like -2 goes into -6 3 times. And also 3x to the -2 can be rewritten as 3 over x squared. And that's probably how we should write it, right there. Okay? But there's your 2 different strategies. They both look very similar, don't they? But it all has to do with the exponents. So when you have an exponent of 1, it's a natural log. And when you have any other exponent in the bottom like that, it is a reverse power rule where you move the term to the numerator with a negative exponent. Okay? All right. Now the rest of them are different. Okay? So part 1 was just how do you deal with these ones that have, a number over x to some power. Okay? But the rest of them are polynomials or more complicated looking expressions. Okay? And there's a variety of strategies that we want to make sure we're familiar with. So let's go ahead and take a look at these. All right. So first of all, how do you know if you need to do U-substitution or not? Well, you're going to use U-substitution when the power in the denominator is 1 more than the numerator. Okay? Or another way of thinking about it, which is just the flip side, it's really just another way of saying the same thing, if the derivative of the denominator is in the numerator. So, for instance, suppose I gave you guys this. Well, let's take a look at that really quick. Look at the power in the denominator. It's 2. Look at the power in the numerator. It's 1. The power in the denominator is 1 more than the power in the numerator. That's one clue that you're going to do U-substitution. And when you do that, this is something you should probably add to these notes, the U is the denominator. So if you're going to go with that strategy, the U will be the denominator. Okay? Now, that's one way, that's how I notice it, but ultimately the derivative of the denominator should give you the numerator. So for instance, if I take the derivative of the bottom here, I get 2x plus 3. Notice how that, if I take the derivative of the bottom, I get the top. So that they'll cancel out. That's the whole point of it. And you might have an extra constant in there or something that you can factor out. But the point is that the derivative, after you take it, should cancel out the numerator. You shouldn't have an x anymore. Okay? So there's that. That would be a U-substitution. So what we're going to do now is I want to take a minute, and I want you guys to look at this page down here, and I want you guys to see if you can find which one of these problems would you do a simple U-substitution for, where you just replace the bottom with a U. See if you can find it. Pause the video, stare at them, see if you can find the correct answer. All right. So is this my U-sub problem? No, it's not, Because look at the power in the bottom. It's a 1, and the power in the top is a 2. The U-sub thing will only work when the power in the bottom is 1 more than the power in the top, and this one's actually 1 less. So this is not my U-sub problem. Let's take a look at number 4. Will this one work? This is the one that will work. Look at it. The power on the x in the bottom is a 5. The power on the top is a 4. I found my U. Okay? So, what I want you guys to do now is we're going to take that problem, we're going to write it right here in this space, and then I want you guys to go ahead and work that problem out. So I'm going to write that there right now. I forgot to look at what it was. 100x to the 4th over 5x to the 5th plus 3 cubed. All right, let's see if I can remember all that. I think that's right. All right, so go ahead and pause the video here and evaluate that integral using U-substitution. When you unpause the video, I will have the solution up for you. So I haven't quite finished the problem yet, but I just want to show you where I've gotten so far. I've got my U, I've done my U substitution. The x to the 4ths cancel out, and 25 goes into 100 4 times. So I should have put a 4 out here actually. Let me fix that. I'm going to erase this. This shouldn't be there. My bad. All right. So this is what we should have right now. So 25 goes into 100 4 times. And so we're left with 4 over u cubed du. All right? Now what do we do? Well, guess what? Now it looks like one of these problems. Which one is it? Is it an ln or is it a reverse power rule? I'm going to encourage you to pause the video once again and finish the problem at this point. And there's our final answer there, circled on the bottom right hand of the screen. It's a reverse power rule because the power is 3, and anything other than 1 is a reverse power rule. So we move the 3 up to the numerator with a negative exponent. We add 1 to the power and divide by that value, which reduces to negative 2. We move the negative 2 to the denominator so that we get this, and then we replace the u with 5x to the 5th plus 3, and our final answer is as you see it there. Okay? All right, let's move on to the next one. The next one is the Trig Functions. Okay? Those ones oftentimes have square roots. Now, it's possible that your U-sub problem will have square roots. So don't get too don't get too comfortable thinking, well, anytime you have a square root, it's going to be an Trig function, because that's not true. Like, for instance, let me give you a U-sub problem that would have a square root. Like, let's say I had this, the square root of 5x to the 4th minus 9. That's got a square root on it, right? The arctrigs are the ones that usually have square roots, but this is not an arctrig problem because look at the powers. This power is 1 less than this, or 1 more than this power. That's a U-sub problem, okay? So I don't want you guys to think that anytime you see square roots, it's going to be an arctrig, but it's something to consider at least, okay? But remember, the main thing is look for that U substitution first. But let's talk about arctrigs. We talked about 3 of them, okay? We talked about arcsine. Arcsine is the one that you get when you're integrating something and it has a 1 minus some variable squared, okay? Arctangent is the one that we have whenever it's 1 over something. This doesn't have to be 1, actually. It could be a squared of any kind. 2 perfect squares that are being added together. And then arcsecant looks a little bit like the arcsine because it has that square root, but you have 2 squares being subtracted and you have an absolute value, or not an absolute value, but actually it won't be an absolute value, take that back. But you'll have another variable on the outside of the radical, like that. So those are arcsecants. So if you see one with a square root and a variable on the outside, it's arcsecant. If you see one without a square root, but they're both perfect squares being added together, that's probably going to be an arctangent. And then finally, if you see one with a square root, but it doesn't have a variable on the outside, that's probably going to be your arcsine. Okay? But remember, just because you see a square root doesn't mean it's going to be arctrig. It could be U-sub. The difference will be that with U-substitution, the power inside the square root will always be 1 less than the numerator. Whereas for arctrig, that's not the case. Okay? So, binomial in the denominator, both terms are perfect squares. Second, if there's a variable in the numerator, it may be a U-sub arctrig combo, and you'll see what I mean by that in a minute. But for now, that's what we're looking for. So, let's go ahead and go down here. I want you guys to see if you can find the arcsine, the arctrig, the arctangent, and I want you to see if you can find the arcsecant. Now, I take it back. I don't want you guys to look for the arctangent right now. But in this problem, there is an arcsecant, and there's also an arcsine. See if you could find the arcsecant and the arcsine. Pause the video and see if you can find them. All right, so arcsecant is the one that has an x in the denominator as well as a square root of 2 perfect squares, and that would be this one. Here's my x outside. Here's my square root with 2 perfect squares being subtracted. So that's my arcsecant. Okay? My arcsine is this one. Okay? I have 2 perfect squares inside of a square root being subtracted. Okay? Now usually there's just a number on the top, but if there's a variable, it's probably going to have some U-substitution involved with it. And so now I'm kind of thinking there is actually an arctangent up here somewhere. My guess is it would probably end up being, there is an arctangent actually, I just found it. See if you guys can find the arctangent. It's hiding. A little bit difficult to see. The answer is number 6. Now the problem is we do have 2 numbers being added together on the bottom, but the problem is they're not perfect squares. Like 5 is not a perfect square, but that, believe it or not, that's okay. We'll work with that. We can actually factor it out. So there's our arctangent right there. Now guess what else? I think this one might end up being an arctangent as well. We'll see. But I think this one's a little bit more complicated because we shouldn't have more than 1 term. When it comes to the Trig functions, you should only have 1 thing in the top. You shouldn't have 2. But I think that we're going to find out that that one's going to end up being an arctan later on a little bit. Okay? But let's go ahead and put all these things in their proper locations. Doesn't really matter what order you decide to put them in. They're all arctrigs, but there they are. And so here's what I want to do. I want to have you guys go ahead and see if you could do these 3 problems. Pause the video, go as far as you can, and when you unpause it, you will see the solution. If you don't know how to do one, skip it, do the other one. I'll give you a hint. For the first one there, the arctan, you're going to factor a 5 out of the denominator, you're going to factor a 9 out of the numerator. But other than that, I'll let you guys go ahead and figure it out from there. So go ahead and pause the video. When you unpause it, you'll see the solution. So the first one there on the left is probably the more challenging one. It has the 9 on the top, which isn't a big deal, but that 5 on the bottom is kind of what messed us up. So the first thing you do is you're going to factor the 5 out so it looks like this. And then you can take the 9 and the 5 out of the integral because they're just constant multiples. And then from there, this fits a nice arctrig or arctangent pattern. And so we have the negative 9/5 followed by the 1 over a, which is the square root of that number, arctangent of whatever's being squared there, which is x, over a, which is the square root of the 1 again. And then in simplest form, we don't really need the 1's there, so we can just get rid of them and have that as our final answer. Okay. The middle one is an arcsecant. The a is 1. So that goes here and here. A is the square root of this number. And then what goes here is whatever number is being squared. So that would be the x. So that's what goes there. And then once again, we don't really need the 1. So there's our answer. The last one was probably the trickier of them all. Now, first of all, what I want to point out to you is that this could not be just a basic U-sub problem. Like, I wouldn't start off by saying, okay, well, U equals 1 minus 4x to the 4th. The reason for that is because this power is not 1 more than this power. It's actually 3 more than that power on the top. So that strategy of just doing basic U-substitution is not going to work. Now, we are going to do U-substitution, but it's not going to be just a straight up U-sub. It's actually an arc-trig U-sub. So let me get rid of all that. And the arc-trig that it matches the most is the arc-sine, because it has a square root with nothing on the outside. Now, if you want to fit an arc-sine pattern, though, you can't have a 4th power here. You need a square. So we rewrite it as a square first. And then we do our U substitution, where the piece that's in the parentheses is our U. So I let U equal 2x squared, which gives me this after we do the du. I replace the 2x squared with U, and the dx with our little du there. And lo and behold, those cancel out. Now I'm left with a nice, simple-looking arc-sine pattern. So the square root of that is my a, and it goes here. This letter goes here. And then we simplify it. We don't need the 1 on the bottom. And then we replace the u with what it was. And there's our final answer. So that's arc-trig. So now we've looked at 2 types of more complicated types of rational expressions. Okay, let's review before we go any further. So we see that whenever the power of the bottom is 1 more than the power of the top, that's just a basic U-sub problem where you make the bottom piece equal to the U. Okay, but if you ever have perfect squares in the denominator, especially if you see some square roots, in those cases you probably have an arc-trig function on your hand to some extent. If it has no square roots and they're being added, that's probably going to be an arctan. And like I said earlier, I suspect there's going to be an arctan in number 9 as well, but we're not ready for that one yet. If you see that there's a square root, but there's nothing outside the square root in the denominator, that's probably an arc-sine. The other one, with a square root but a letter on the outside and the bottom, that's an arc-secant. So there's our review so far. Let's go ahead and deepen our understanding a little bit, though, because we've got a little bit more to go. Those are the 2 most common ones. Now, the last 3 are not very common ones, but they get mixed up a lot with the first 2 that we talked about. Now, those first 2 we talked about are really common, especially the basic U-sub. You see that all the time. Arc-trigs once in a while. These next few, completing the square and long division, well, they're not really popular. They pop up here and there, but we'll talk about them. Splitting the numerator is fairly popular, though. Well, we'll talk about that. Now, let's see if we can identify those. So, completing the square. That happens usually when you have a trinomial in the denominator. So if you ever have a 3-termed expression, like let's say you have this, x squared minus 5x plus 1, and maybe just a number in the top, I don't know. But if you have a trinomial, then it's possible that's going to be a completing the square problem. Now you probably might be having a little trouble remembering that because we did that a while ago, but I'll remind you. I'll give you an opportunity to figure it out again today. Long division, that's what we talked about last time. When you have a polynomial in the numerator who has a power higher than that in the denominator, that's a long division problem. And then finally, we have splitting the numerator. That's when you have a polynomial in the numerator with a power that's lower than the denominator. Okay, so you have more than just one term. There's multiple terms in the numerator, but the numerator has a lower power. So long division and splitting numerator look very similar. The only difference is the powers. For long division, the bigger power is in the top. For splitting the numerator, the bigger power is in the bottom. Completing the square is a very special circumstance where you actually have 3 terms in the denominator. So here's what I want you guys to do for these last 3 is I want you to come back to this page here, take a minute and see if you can figure out which one of these is a numerator split, which one is a long division, and which one is a completing the square. Well, not surprisingly, we could ignore this one, this one, this one, and this one, because we've already done all those, so we're just left with these three here. So which one is which? Well, let's take a look at number 3. So we have a polynomial on the top with a power greater than the bottom. This is our long division problem. The next one here, number 5, that one has a polynomial on the bottom only, and it's a trinomial. So that one is a completing the square problem. And therefore, this last one here, notice that we have a polynomial on the top and bottom, and the one on the top has a smaller power than the bottom, then that's going to be a splitting the numerator. Now, real quick though, some of you guys might have noticed back on number 4, well, remember when we said U-sub? U-sub is when the term on the bottom has a power that is 1 more than the top. Well, that kind of is true here, but you're going to find that if you tried U-substitution, it's not going to work completely. Now, there's a reason right now that these do have that situation, and that's a nice little hint. Somewhere along the way, we are going to do U-sub, but I just guarantee if you try it, it's not going to work. And here's why. We take the derivative of that, right? And that's going to be 4x cubed, so we're going to have this, right? Well, is this going to cancel all that out? The answer is no. So even though it kind of fit our U-sub pattern there, something's not right yet, and that's why it's a splitting the numerator question. Remember also how I told you this one also kind of looked like an arctangent? So guess what? This one is really 3 problems in one. It's a splitting the numerator problem, and after we split the numerator, it's going to be a U-sub because of this, but it's also going to be an arctan because of the sum of the perfect squares. So there's actually going to be 3 problems on that one. But anyway, so we're not wrong to notice that this one fits those patterns, but we got to get the order right. And in this case, splitting the numerator is going to take precedence. So let's go ahead and put them in the right places on the first side of this sheet. So there's our example there. All right, so now I want you guys to actually work these problems out. We haven't done completing the square in a while, so you're going to probably have to look at your notes or something to review it, but if you remember it, awesome. But go ahead and pause the video, try it on your own first. It's important you guys try it and don't just watch me do it, because that gets kind of old. But before you start, we need to make a little correction here. This will not work out if I have the numbers up here that I currently have. So we're going to make a little change. I want you to change this 7 into a 25, I think it is. Yes, that'll work. So we're going to change the 7 into a 25, okay? Now I want you guys to pause the video here and try the completing the square, and when you're done, unpause it and I'll walk you through it. But try it on your own first. That's important, because watching me do it isn't going to help as much as you actually practicing it. Okay, so the first thing we do when we're trying to complete the square is we're going to add 2 new numbers in the denominator. One is going to come here, and one's going to go after the 25. So one before and one after the 25. And what that number is going to be half of this number, but squared. So half of 8 is -4, and if you square it, you get 16. And that's what you're going to put here. Now for this one, you add it, but on this one, you subtract it. Okay? And the next part we do when we're completing the square is for this trinomial, we're going to factor it. Now that's a perfect square trinomial, and I gave you a shortcut for factoring it. It always looks like this. The only thing we have to find is what number comes after the x, and that is always going to be half of the middle number there, so it's going to be -4. The next thing we do is we need to put these together. So 25 take away 16 is 9. Okay? Now, at this point, we've done the completing the square strategy, and whenever you do the completing the square strategy, it always turns into a U-Substitution Arctan problem. So that's where we'll go from there. So the U is x minus 4, which means that du equals dx. And so we do our U substitution here. I'm going to pull the 4 out to the front. The x minus 4 becomes u. And now we're ready to go ahead and do our arctan integration. So we have 4 arctangent. Actually, I take that back. Let me back up a little bit. The 4 is just there, but so the 4 is going to be there, but then when we integrate this, it's 1 over a. The a is the square root of this number, which is 3. Arctangent of u over a. And we don't want to forget our plus c. And we're going to put our u back in as x minus 4 now. Now in this case, I'm going to just you multiply the 4 times the 1/3. And so your final answer would be 4/3 arctangent of x minus 4 over 3 plus c. Okay, so that's a completing the square example. So that takes care of this one. Let's move on to the next one. Go ahead and pause the video and try the long division problem. And when you unpause it, you will see the solution worked out. Okay, so at the top, I've shown you my long division. And then whenever we rewrite the integrand, we get this because of the long division. When you integrate x, you get that. And when you integrate 2, you get 2x. And for this one, we're going to have to just do it separately. It's a U-sub problem. Because why? Because the power on the bottom is 1 less than the power on the top. The power on the top is 0 for the x, because there is no x. And then we have a power of 1, x on the bottom. So that's a U-sub problem, which I've got my u over here. And pulling the 11 out to the front and doing my U substitution, I end up with 1 over u du. Then the integral of 1 over u, whenever the power on the bottom is a 1, that's an ln problem, right? Talked about that earlier. So we actually end up with negative 11 ln of u, which is x plus 2 plus c. All right, and so there's our final answer for that one. One more problem. The next one is a splitting the numerator problem. So we finished that. Now we're going to move on to that. So go ahead and pause the video and go through as much of that as you can. So there's the first step, is to go ahead and write it as 2 separate integrals and separate fractions. Now we get to make another decision. Now that we've done that, now we can ask ourselves, what integration strategy would you apply to each one of these? How about this one? I'll give you a hint. The power on the bottom is 1 less than the power on the top. What strategy is that? That's a U-sub problem, where you make the denominator your u. All right. How about this other one over here, though? So I'm not going to finish that just yet. I'll have the solution up in a minute. But for now, let's take a look at the next one. Well, the power on the bottom is bigger than the power on the top, but they're not 1 apart. And the only other one that is matched so far then would be one of our arctrigs. Now, the only way this is going to match an arctrig, though, is if it's arctangent, because they are 2 perfect squares that are being added together. But as you know, arctan only works if you have squares on the bottom, not 4th powers. So the first thing you want to do for this one is rewrite it as a square instead of a 4th power. And so I've got you started with the first step on each of these halves. So for the one on the left, you're going to do a U substitution with that as your u. And for the one on the right, you need to rewrite it so that it's not x to the 4th, but it's something squared. And whatever you get for that something, that will be your u for that problem. So go ahead and pause the video again if you haven't gotten that far and see what you guys get. When you unpause it, I'll have it completely worked out. And there's the rest of the problem. So I did this one problem here on the left, and this other problem here on the right. And then the final answer, when you put them together by adding them at the end, is what you see there circled at the very bottom. Okay? And so now we've kind of done a nice little review of all the different strategies for finding integration or for finding integrals that we've learned so far. So keep this sheet. Nice little thing to put in your notes, maybe even particular at the very front of Unit 2 of your notebook. That way you can always have it to reference, because later on it'll be nice to come back. Oh yeah, how can I tell which one is which again? This one is a great little resource to have to tell all those different integration strategies apart. Anyway, till next time, see you then.